key working parts of the natural treatment system. This is if you had X-ray eyes and you could look inside the system and see how it's set up. But you can see from this view that we have a surface layers, several layers of constructed media. These are different layers, different types of sands and gravels, and with a system of distribution of pipes on the surface and a system of collection pipes and chambers on the bottom. Flow comes in through the dark black line on the top here and spreads laterally out across the top of this media bed. That flow is designed to be pulsed and allow water to enter that media matrix and settle down through there, coming in contact with a biologically active media bed. This is comprised of naturally occurring soil bacteria and fungi, the things that we find already in the soil water anyway, and that provides a treatment. These bacteria use that glycol, use that VOD that's in that water as a food source. They are consuming that naturally and passively, and it's there as they've evolved to do over time. Our sizing is such that we've built it so we can take and treat a large portion of that flow and process it to a good quality water. As it falls down through the system and gets collected at the bottom in the first stage, it then discharges to the next stage. That, as I showed you before, 2 steps in series. Well, that's a very fortuitous design for actually getting a good level of treatment, making it more efficient as you go from stage to stage. This system here is designed to be passive and operationally simple, designed to achieve high levels of treatment of VOD, and with really relying only upon the power of gravity and the evolutionary history of these bacteria to provide that treatment. So that system will be set up so that it discharges down to the river. There'll be several monitoring locations along the length of that flow path. There'll be a monitoring location east of the highway where we can sample for flow and composite sample for the water quality itself. There's a second sampling location for monitoring at the discharge to the outfall to the river, where we can sample the dissolved oxygen and confirm that we're meeting the state standards in that discharge to the river. We also intend to sample and monitor the natural treatment system beds themselves during their operations. We can confirm their operation and obtain that information and confirm its operation and performance. So I'll turn it over to Dean Emeritus from Mead and Hunt, and he'll provide an overview of the general approach to take.
Thanks, Jim. So Jim just described really what's the heart of this system, and that's the natural treatment system. Biologically driven, specifically designed to remove the deicers and purify the water before it's discharged to the Thornapple River. What I want to talk about now is the different phases that the airport has been through in terms of its deicing system and discharges. Way in the past, basically pre-2000, from 2000 to today, and then what we anticipate in the future. And I really want you guys to pay attention to this because this describes the expected benefits of this system to the Thornapple River, in fact, to the environment in general. So as you can see on this slide, we've got 3 time periods. The time period prior to 2000 when the airport was operating under a general stormwater permit issued by Michigan DEQ. From 2000 to the present, where the airport's been operating under what's called an individual industrial stormwater permit, much more specific requirements that are tailored to the airport. And post-project completion, 2015 and beyond, when the airport's going to have the new system in place and a new, more stringent set of requirements goes into place associated with that system. So, prior to 2000, the bottom half of this slide, there were just nominal, very rudimentary BMT controls on deicers. In spite of that, and we know this because DEQ required it at the airport, a study was done in 1999, published in 2000, where the airport was told by DEQ to go monitor dissolved oxygen in the Thornapple River. They were concerned that the deicers were causing excessively low concentrations of dissolved oxygen in the river. The airport asked DEQ, where do you think it's going to be the worst? The DEQ modeler, who's going to be here next week to talk about the details of their current analysis, suggested a number of locations in the system. The airport went out and bought continuous monitoring equipment, deployed that equipment for the winter, and captured a number of fairly large de-icing events, not only during the event, but for about a week afterwards, continuously monitoring dissolved oxygen at those locations. What we found was an essentially imperceptible change in dissolved oxygen in association with that de-icing event. Okay? That's an important fact to keep in the back of your mind. That's before any of these controls in the last 12 years were put in place. So during that period, what happened to de-icers? Well, there were basically two different destinations for it. Whatever made it into stormwater discharges, and the second component, what's commonly termed in the industry fugitive or non-collectible. It's become apparent to me that we have not done a very good job of describing this accurately, because there's a word missing from the definition, and that's lost on site. There's a certain fraction of de-icers that never makes it past the boundary of the airport, and that boundary is whether you're talking about the water boundary, the soil boundary, the air boundary. The reason for that is these are extremely biodegradable materials. That's one of the reasons we can build a wetland treatment system, a natural treatment system, and so effectively treat them. They're great food for microorganisms, whether they're sitting in that NTS or if they're occurring out in the soils and the turf and the pavement of the airport, which in fact is exactly where those bacteria come from when they come and populate the natural treatment system. So what about the second phase, from 2000 to the present? Starting in 2000, the airport started implementing de-icing controls. The initial ones were fairly rudimentary because they had to get something on the ground quick. They used a street sweeper for collecting the glycol. They had very rudimentary blocks in the catch basin inserts to trap it on the surface before they could collect it. In subsequent years, they went out and bought specific equipment that's specifically designed for collecting glycol. Over those years, they installed something like 47 or 48 purpose-built drain blocks to make sure that the glycol was trapped on the surface and then the trucks could come by and sweep it up off the surface. We also were mandated to do testing and monitoring. Monitoring all de-icer usage at the airport and monitoring what was leaving the airport in terms of stormwater discharges. We were also monitoring what was going to recycling, because that's where the collected glycol was going. As summarized in that last block then, the three destinations for glycol during that 12-year period were stormwater discharges, that fugitive, uncollectible lost fraction, and the collection and recycling. And the recycling is hauled down to Romulus, Michigan. We're taking advantage of a program that's set up there to support the Detroit Metro Recycling Program. So it's very fortuitous that it was located that closely. And then from 2015 onward, with the new project in place, we're going to continue with the best management practice controls. The current permit requires an annual review. How well are we doing? Could we implement improvements? What's going on in the industry that we might adapt at the airport? We're going to continue that process. Nothing's going to change. We're going to continue to look for improvements in that system. We've added treatment, and I can't emphasize this enough. This is not just a simple sand filtration. This is biological treatment. We're building an on-site treatment plant to deal with this de-icing runoff. And now we've got a fourth destination possible for de-icers. Again, something's going to go to stormwater discharges. We're going to have that fugitive, uncollectible fraction that's still something that's a fraction of what's been applied. It's uncollectible, and basically it's biodegrading on site, or it's getting carried off on aircraft. And if you've got detailed questions about that, I'll be glad to answer it in the Q&A. We've got the continuing collection and recycling. We're not going to give up on that. We believe it's the right thing to do with glycol because it's recycling it, making it's avoiding the need to produce new glycol from petroleum stocks or whatever. And then lastly, the fraction that's going to be removed by treatment. So let's look at some numbers to be specific. The fugitive, uncollectible, lost on site, we're estimating at 36%. We just didn't pull that out of air, we didn't pull it from another airport. We actually did monitoring at the airport, where we knew how much was applied to the aircraft. We knew how much was collected and hauled off for recycling. We knew how much was being discharged at the stormwater outfalls. And from that, we could tell how much we couldn't account for, and that's the fraction that's lost on site. And that worked out to about 36%. Interestingly, it's on par and very comparable to what other airports are seeing. Just this last winter, Detroit Metro, which has one of the most aggressive monitoring and accounting programs for their glycol in the nation came up with a number of 37.7% fugitive lost on site. So we're right in that same ballpark. And now I won't go into a lot of detail, but where does it go? Well, it's a combination of evaporation, a lot of natural degradation on site, and a certain amount remains on the aircraft. These fluids are designed, they're engineered to stay on the aircraft to ensure safe takeoff and operation under winter conditions. So prior to 2000, again, what's the breakout of that? Based on the calculations, the monitoring and so forth, we estimate about 36% fugitive, uncollectible, lost on site, and roughly 64% available for stormwater discharge. Let's look at then what about the collection and recycling? This is a particularly well-controlled portion of the project because we know how much is sprayed on the aircraft with a high level of accuracy. We darn well know how much is hauled off because the hauler is charging us for the volume, and they're keeping very close track of the concentration of glycols in that material. What we've seen over the past 12 years that we've been doing this is first of all, the first couple of seasons we saw a steady increase in our recycling. And then we sort of plateaued out with variability from year to year. And that variability is largely driven by the kind of winter we have here. But overall, it's about 28% average. And I have to emphasize, that's 28% that's kept from going into stormwater. So what's that look like numerically for the present conditions? Again, that 36% fugitive. Collect and recycle is now 28%. The remainder goes down to 36% being available for stormwater discharge. What about the treatment system? This is a little complicated, but I'm hoping to keep it simple. That 29% is 29% of all the de-icer that's applied on aircraft at the airport. And it's based on that natural treatment system removing 80% of the de-icers that come into it. And the fact of the matter is, you're not going to be able to detect de-icers leaving that natural treatment system, but the water will still have the biochemical oxygen demand, which is the principal environmental concern, remaining from the de-icers. But you won't be able to detect propylene glycol. All you'll be able to detect is the biochemical oxygen demand. And I think that's a really important detail to know. As mentioned earlier, we've got a detention basin built into the system. Its function is multiple. One is just to meter the water into the treatment system so it's operating at optimal flow. We've also designed it to remove sediments because we listened. We heard the neighbors being concerned about sediment erosion control, so it's been designed to settle out the sediments. We also heard concerns about trash and floatables in the airport stormwater, so we're building in trash removal capabilities into that detention basin. So it's a multi-function basin. Post-project collection, what do the numbers then look like? Again, we've got that lost and fugitive fraction. You'll notice that's not changing because we're not changing anything in those processes that occur out on the airport. They're beyond our control. We're going to continue to collect and recycle. We got 28% here. We might be able to do better, but right now we're feeling comfortable we're going to be able to do at least that well. Treatment removal works out to about 29% of the total, and what that leaves is 7% of the remaining, 7% of the total applied being available for stormwater discharge. And again, it's not going to be as propylene glycol. It's going to be as some partially treated amount of that, but it still represents the biochemical oxygen demand. Just to put that graphically, what we show here is those 3 different periods, and each of the bars represents the different components. Let's really focus on the bright blue bar, because that represents what's ending up in stormwater. Okay, and you can see there's a pretty darn dramatic decrease from pre-2000 to when the on switch is flipped on this system.
Dean, if I can have you wrap up.
At this point, I want to thank you guys, and I'm going to leave.
Perfect timing.
You can feel that in the back of the
Yeah. Thank you.
You can go up and get yours loaded up if you want, Jim. We're all set. This is our last slide. I just want to again thank everybody for the opportunity to be here tonight and just point out one thing. One of the slides early on talked about the proposed project, and our program cost for this project is estimated at $22.2 million. Now that includes all the work that has been done so far to date, and the estimated construction cost is right around $18 million. And I just want to indicate that we've been working closely with the FAA. This project is eligible for grant funds for the FAA, and so we anticipate about 90% of the cost will be covered by federal grants. And again, just thank you. We'll be glad to stick around as long as we need to tonight for a Q&A. Appreciate it.
Thank you.
Wow. Good evening, and welcome to the first public meeting to discuss the proposed aircraft de-icing fluid management and stormwater discharge plan for the Thornapple River related to the Gerald R. International Airport. My name is Jim Dixon. I'm a professional engineer registered in the state of Michigan, and I have been practicing environmental consulting for approximately 25 years. But more importantly, I am a native of southeast Kent County. I grew up in Ada and Cascade Townships, and I currently reside in Caledonia Township. I've spent many of my days on the Thornapple River and its tributaries doing various recreational activities. The Thornapple River is an extremely important and valuable natural resource to us and our community. Approximately 2 years ago, I was contacted by the two river associations to take a look at the Trout Creek incident and try to assess and get a better understanding as to what is going on with the discharge there. I've spent the better part of the past 2 years meeting with various individuals, talking to the DEQ, meeting with the airport, doing research and conducting my own assessment of what is going on, using my tools of engineering and environmental consulting to move forward. What I found out was pretty enlightening as far as discoveries. My purpose here today is not to point fingers or say somebody's doing something right or wrong. It is to more or less bring this information to the table so that we all collectively as stakeholders can make some intelligent discussion, have some discussions and make some decisions on the fate of our Thornapple River. So to start with, approximately a year ago, we prepared a little video summary that more or less does a very good job of providing the problem and also provides some analysis of Trout Creek, of what is going on currently. So I'd like to roll that. It's about a 2-minute spiel, and we'll circle back and do some further analysis after that. Go ahead, Jill.
Like all airports, the Federal Aviation Administration mandates that the Gerald R. International Airport must have a program to seasonally de-ice airplanes during 8 months of the year. Aircraft de-icing fluid, or ADF, is a chemical mixture used not only to de-ice the aircraft, but also to delay the reformation of ice for a certain period of time. The main ingredient in Gerald R. Ford International Airport's ADF is an organic compound identified as propylene glycol, or PG. PG is well known for its antifreeze properties, but it is also unique in that it serves as an alcohol solvent and reducing surfactant. In other words, PG has the ability to dissolve certain hazardous substances and break down large molecules, such as oil and grease, making them extremely mobile. This gives PG the ability to essentially absorb or carry almost anything it comes into contact with on the tarmac. The tarmac substances that can be mobilized by PG include oil, fuel, solvents, salts, fertilizers, herbicides and pesticides, metals, scrap rubber, and countless other products that contain hazardous substances. PG in itself is known to naturally degrade in both aerobic and anaerobic conditions, but the process is taxing on the surrounding environment. The compound maintains high levels of biochemical oxygen demand, or BOD. In essence, BOD is a food source for many of the organisms and plant life within a waterway. When an organism or plant uses the BOD, oxygen is consumed as part of the process. The problem with PG is that the oxygen depletion potential is 100 to 1,000 times greater than that of raw sewage. In other words, the amount of PG used during a single jet airplane de-icing event can be equivalent to the BOD loading of 1 million gallons of raw sewage. This causes dramatic degradation of water quality and disrupts the health of the ecosystem. Other related issues to PG in a waterway include extensive chemical and foul odors, turbidity, discoloration of waterways, foaming in the waterway, biofline blooms, and the displacement or elimination of certain native aquatic species.
So that did a very good job of explaining the situation. I think we've come to the conclusion that propylene glycol, PG, is not a friendly substance. PG is also regulated as a hazardous substance under Michigan Public Act 451, Part 201. There is a cleanup criteria for the soil and groundwater for this substance as it hits the ground, as it hits our waterways. PG is an alcohol. PG is an excellent solvent, as we described in the video, capable of dissolving and carrying pretty much anything it comes into contact with on the tarmac. Some of the observations that I discovered and noticed over the last couple of years, the DEQ did a characterization survey of the stormwater discharge February 2012. The results of that showed that there was methyl ethyl ketone in the discharge, as well as some metals. The MEK is not disclosed on the Stormwater Pollution Prevention Plan. The source of that MEK is unknown. It provides us with questions as to the characterization, the full characterization of what is in that stormwater. In addition to that, we've collected some independent metals of ran some metals analysis of the sediments at the Trout Creek outfall of 001 down by the Berger Bayou, and we've also recently done some work in the Plaster Creek outfall 007. And what we're finding, there are metals that appear above the drinking water protection criteria and also the groundwater surface water interface criteria. That data is presented on one of our poster boards outside if you'd like to take a closer look. In addition, 15, 20 years ago, there were previously 4 wetlands that received the stormwater discharge where the cargo hangar is and the north-south runway. 3 of those 4 wetlands contain metals, heavy metals, that required remediation prior to filling. So the observation of metals in the discharge is a pretty common phenomenon associated with airports, and we have documented that historically in this one too. Again, the full characterization of the problem seems to be an issue. As the slide, as everybody has gone through, PG has excessive oxygen demand. The de-icing fluid used to de-ice a jet airplane can be the equivalent of 1 million gallons of raw sewage. I'm a big visual guy. I like to show things visually. If you want to understand what 1 million gallons looks like, it's approximately a football field, 300 feet by 160 by 8.4 feet deep.